ahead and start. So what I want to do now is we've talked about and understood series circuits. We know in the series circuit there's one path for current and there's many voltage drops. We talked about the difference between a voltage source and a voltage drop. We also talked about what happens when you put batteries in series. You put batteries in series to increase voltage. We talked about parallel circuits. We understand that in parallel circuits, the voltage is the same across every parallel branch, but then they have different currents. The branch currents add up to the total current. And so we learned about parallel analysis. So now what we like to do is put the two together. We like to put the two together into a circuit called a combination circuit or series parallel circuit. And so what you have to do is make sure that you understand the series concept and make sure you understand parallel. You put the two together, and the learning curve for going to the series parallel shouldn't be that steep. If you're not good doing series and you haven't practiced parallel enough, then this is where things are going to start to get a little hard. Just kind of looking ahead, what we want to do is most circuits are actually series parallel. Most circuits are series parallel, so we want to learn the analysis for a circuit that's series parallel, and then we're going to put multiple voltage sources in those circuits. And at that point, we can't use just Ohm's law to solve the circuits anymore. We gotta resolve the more powerful mathematical techniques that we'll talk about in the weeks to come. So that's kind of where we're headed. Before we get into all of that, I have a new term for you that I want to talk about. Node. The term node. And it's kind of hard to define it. It's easier for me to show it to you. Here's what I mean by node. Let's say I have a circuit. Like that. And I'm going to draw just a circle, or not a circle. I'm going to draw this shape. I'm going to call it a circle. It's not really a circle. I'm going to draw that circle around these wires. Those wires act, let me label these. This is R1, this is R2, this is R3. So if you look, you'll see that this circle is cut by 3 different wires. So like it's cut right here, it's cut right here, it's cut right there. So if you have a connection of wires and it's cut by 3 or more wires, if you can draw a circle around it and that circle is cut by 3 or more wires, then we call that connection a node, N-O-D-E. So I got to have at least 3 wires. I can have more. There can be other ones cut in the circuit, but I got to have at least 3 of them. Now, when you have a node, it will always define, at least for what we're doing right now, it will always define things in parallel. It will always define components or devices in parallel. And what I mean is R2 and R3 are in parallel, right? R1 is in the picture because it makes up the node, but I got to have something in parallel branches. Something has to be in parallel for me to have a node. So let me redraw this. I want to refer to something else that has to do with the node. This is called a node voltage. A node voltage. So again, I'm going to draw the circuit like I had before. Now there's actually 2 nodes here. I'm going to circle the nodes. Here's the node right here. And here's a node right here. Now the node on the bottom I stopped it right here, but electrically it actually goes all the way over to here. As long as I don't hit a resistor, the node extends. I'm just not showing it. Like right here, that node actually extends to that point. Doesn't go over here. That's a different wire. But I can draw it all the way over to R1. But typically what you want to do with nodes is encompass things that are in parallel. And so I'm kind of showing that. I'm just kind of circling the parallel part of the top of R2 and R3 and the bottom of R2 and R3. Now, what you can do with this, if I want to talk about the voltage, now remember what we said about voltage drops. Voltage drops exist across a resistor. If I want to name a voltage drop, I name the voltage drop after the resistor. So if I want to talk about the voltage drop across this resistor R1, I will call that voltage drop V1. If I want to talk about the voltage drop across R2, I will call that voltage drop V2. If I want to talk about the voltage drop across R3, I will call that voltage drop V3. Now, what do we know about V2 and V3? What do we know about those two voltage drops?
They're the same.
They're the same. Why are they the same?
They're in parallel.
They're in parallel. Parallel devices have the same voltage. So I can say that V2 is equal to V3. And another way of naming these, though, is I can actually name the nodes. I can say, all right, I'm going to call this node A, and then this node B. And if I name it, I can call it V, A, B. And the way you read that is the voltage from A to B. And automatically, when you see a voltage named that way, you know you're dealing with something in parallel or something that's been in parallel, right? This is a node voltage. Nodes only encompass things that are in parallel. And we know we're talking about something that's in parallel. If you know that's a node voltage. It could be voltage from point A to point B, but if I tell you that's a node voltage, then automatically you know we got things in parallel just by looking at it. So instead of naming V1, V2, and so forth, I can just say VAB, and that VAB exists across both R2 and R3. Does that make sense to everybody? John, you're the only one I can see shaking your head because everybody else has their cameras off. So I'm assuming you guys are doing this. It makes sense. Okay.
Yeah.
All right, now, thank you. From this point on, guys, listen. From this point on, you must color code everything. Part of the requirements for the class is you have to have coloring pens and pencils, and you have to have a straight edge. Here's where you need that stuff. You'll see these circuits are going to blow up. And these circuits are going to become really complicated if you write everything in the same color. It's going to be a nightmare trying to keep things straight. So here's where neatness, color coding, all of that's going to count. It's going to pay off for me and for you. So from here on out, anything you hand in to me, any of this stuff we're doing now has to be color coded. Now, what do I mean by color coded? Well, what I tend to do, and you kind of see me do it already, but since we're going to more complex circuits now, you'll see me do it more. I write all my voltages and voltage drops a certain color. All my currents will be a certain color. My power, anything I'm showing will have its own color, so I can just not only look at the mathematical symbol, but from that color, hey, that's red, I know that's a current. Hey, that's blue, I know that's a voltage drop. You don't have to use my colors. I'm just saying be consistent, so when I look at your work to grade it, I can see all his voltage drops or her voltage drops or a certain color. If I see blue, I know he's using blue for voltage drops. These circuits are going to become complex, and it's just going to look like a bunch of scribbles. But if you color code it, I can actually see where you're going. I can see your logic, and that's what I want to be able to do. So from here on out, don't come to class for an exam, quiz, any of that. I'm not telling you don't come to class, but when you come to class, you must have your coloring pencils. You must have your calculators, all of that stuff. So any questions over nodes? Let me show you what can happen with a node. Let's say that, I'm just going to redraw the circuit a little better over here. Let's say you got this circuit. Actually, let's just put numbers in. I'll put numbers in. So let's say I have I got 3 resistors, R1 is 2 ohms. R2 is, let's make it 3 ohms. And R3 is 6 ohms. So I got that circuit. And what I want to do is, let's put a voltage source over here. So I got this circuit. And the first thing I want to do is I'm going to identify the nodes. So I got 2 nodes. I got one right here. I got one right here. I'm going to call this node A. I'm going to call this node B. Now, there's something called an equivalent circuit. The term equivalent, what does that mean? When something is equivalent to something else, what does that mean? How would you define that? How would you explain equivalency to a kid? What does it mean?
It's equal to. Matches.
It's equal to or has the same value, but the form is different. You know what I'm saying? It has a same value, but the form of what we're talking about is different. So, for example, a paper dollar bill is equal to 10 dimes, but they're different things, right? They're different forms. They have an equality between them, but they're different forms. An equivalent circuit is a circuit that has the same resistive value, but you can have different number of elements of resistors in it. And this will be clear when I show you. All you got to do is just find we can start combining things. So I can redraw this. So I'm going to redraw this. Now watch how I do this. I'm going to redraw it. But what I want to do is I'm going to combine things that I can combine. And the thing that jumps off, just right off the board that I can put together as one, make it one, would be R2 and R3. Clearly you can see R2 and R3 are in parallel. So I'm going to redraw this into an equivalent circuit. So I'm going to draw this. That's this. That's R1. But these two I can combine. Now, the way I'm going to show, this is I'm going to name this. I got R2, and R2 is in parallel with R3, so I'm going to use this operator right here to represent parallel. I use a plus sign to represent series. I use that sign right there to represent parallel. So if I do this, oops, I'm trying to tell you that R2 and R3 are in parallel. And you know either use the 1 over R rule to find the total, or use the product over sum to find the total. Some kind of way you got to find the total, but this is the name of that total. So I'm going to combine these into one. So I'm going to draw one resistor here. I'm going to call it R2 parallel R3. Now, what is R2 parallel R3? What is 3 parallel 6? Do the math for that and tell me what it is. Anybody got an answer?
We're adding them together?
These are in parallel.
Right.
R3 parallel R6. So this
Two.
sign right here is parallel. So what was your answer?
2.
2 is the answer. So now how do we get to it? Well, I can use this one, right? I can do 1 over REQ equals 1 over R1 plus 1 over R2. Well, R1 is 3, R2 is 6. And remember I showed you that reciprocal key? You do your 3, hit the reciprocal key, that automatically divides this into 1, plus 6, hit the reciprocal key, and then you hit equals, and what you'll get, or what you should get as an answer, is 0.5. That's not your answer though, that's 1 over R, that's actually the conductivity. And the way you get your calculator to give you the answer real quick for REQ, you hit your reciprocal key one more time, and you should come up with REQ of 2 ohms. You could do it that way. Now, if you don't understand how to use a reciprocal key, either, I don't know, when you come to lab, I'll show you on your calculator. You want to be able to do that quickly, because here's what happens. All my exams are, well, a take-home exam you can take as long as you want on it, as long as I sign. But the in-class exams are 1 hour. And on the last exam, you know, you guys, a lot of you use the whole time, but the problems don't get any simpler. They get bigger. So you got to be able to do problems faster. So anytime you can save a keystroke or anything on your calculator, that adds up in time, and you want to be able to get through it a little quicker. So that it kind of helps if you can do it quickly. Another way to do this, though, is to use the product over the sum rule. I got 2 resistors here. So another way to solve it would have been to take the product of the 2 resistors over the sum of the 2 resistors. So the product, I have 2, no, I have 3. I have 3 times 6. I got a 3 and a 6, and the sum of the 2, I got a 3 plus a 9. Product over sum. On the top, I get 18. On the bottom, that should be 6. On the bottom, I get 9. 18 on 9 is 2. Either way, you get 2. So that 2, I'm going to write here. So here's the 2. So this is an equivalent circuit to this. Now listen. It's an equivalent circuit from the point of view of the battery. That's important. This and this are equivalent from the point of view of the battery. As a matter of fact, that battery doesn't know how many resistors are hooked up. If the battery could think, if it could not see but it could think, it can't tell if this is what's hooked up. It can't tell if this is what's hooked up. It can't tell if 2 plus 2 is 4, if there's 1 4 ohm hooked up. It can't tell if there's 4 or 1 ohm. It doesn't know. All it feels is 4 ohms of resistance at its terminals. From this point to this point, it feels 4 ohms. But it doesn't know how the 4 ohms are configured. The point, though, is that this circuit and this circuit is equivalent from the point of view of the battery. So I can put the battery right here. And if I took that battery off of this circuit and put it over here, it can't tell which circuit it's hooked to because both circuits feel the same. It feels 4 ohms of opposition. Equivalent circuit. But the point I'm making is, where are my nodes in the new circuit? Where's node A in the new circuit?
It would be the top right corner.
Exactly right, right here. Node A is right here, and node B is right here. I know that this thing right here gave me this, right? And at the top of this thing right here was node A, so it's still there. And at the bottom of this thing right here is node B, so it's still there. But over here, we say the nodes are collapsed. The nodes are collapsed. So I have collapsed nodes. I have expanded nodes right here. And if I talk about the voltage in the equivalent circuit, if I talk about the voltage from A to B, what I like to do when I show a voltage drop, you see me do it. I like to draw a little circle that represents the voltmeter and show the leads come up to the points I want to measure between. So if I was talking about measuring the voltage from A to B, I might do something like this. Voltage from there to there. Well, that voltage, if I drew it over here, that voltage at B would go from node A to node B. Because you know, anytime you see nodes, that encompasses something that was in parallel in an equivalent circuit that came before it. So anytime you have that, an equivalent circuit, got 2 resistors in parallel, you go back to the original circuit, those parallel things are going to have the same voltage across them because that's the definition of a parallel circuit. They got to have the same voltage. So this idea of a node, we're going to use this extensively as we solve more complex circuits. So look at this circuit right here. Look at this circuit. And I'm going to draw it. Draw this on your paper, guys. You need a piece of paper. And on your paper, you need like a typing paper or notebook paper. Draw this circuit. Draw the circuit this one right here, figure 6-6. Draw it in the upper left-hand corner of your paper. You want to leave yourself some room because you're going to redraw this over and over again. I'm going to show you what I'm saying, but draw it in the upper left-hand corner of your paper. Take out a piece of paper and draw that first circuit in the upper left-hand corner. Now make sure you're not just watching the video and I can't see what you guys are doing. Please make sure you're doing what I'm saying right now, because if not, things are going to get complicated for you. I want you to go through the steps and kind of feel what it feels like to solve a problem like this. So don't just sit there and listen to me. You gotta play the game here. You gotta draw the circuit and participate. So draw that circuit on your paper in the upper left-hand corner.
Excuse me, sir.
Question?
So which one we need to draw?
Wait a minute, hold on. Let me turn your volume up. I can't hear. Say that again. Is that right? What'd you say?
I say which one we need to draw?
Oh, we're drawing a figure 6-6.
Okay, thank you.
Figure 6-6. You're welcome. All right. So here's the circuit. Couple things about the circuit. First of all, it should be clear to everybody looking at this that R2 and R3 are what?
In parallel.
They're in parallel. That means that they're connected to a node. So we know we got two nodes to deal with. It should also be clear to you that R1 and R4, now listen to how I say this. Listen, R1 and R4 are in series with the parallel combination of R2 and R3. Would you agree with that? I said R1 and R4 are in series with the parallel combination of R2 and R3. You see it?
Yes.
And R1 and R4 are in the main lines. Now, what do we know about the main line of a circuit? What do we know about the main line? The main line carries the what?
Voltage.
Not voltage. Voltage doesn't move.
Current.
Current.
Correct.
The main line, remember I told you about your fuses in your house, your circuit breaker? You got all those circuit breakers for each room. Everything in the room is in parallel. All the outlets, the light bulbs, that's all in parallel. That's a room, right? So I can put a circuit breaker for a room, but also I can go in my basement and there's one that called the main. I can click that one, and that turns everything in the house off. That's in the main line, coming right from the telephone pole to your house. That's the main line. You cut the current in the main line, everything goes off. So remember from before, from the parallel, the main line carries the total current. I got two main lines because I got two terminals they're connected to. I got this main line and I got this main line. And what I know is that the main line carries the total current, and the only difference between the two main lines is if the current in this main line is going this way, and then this main line's got to go the other way. So when I'm solving a circuit like this, anytime I find the current in this main line, automatically I found the current in the bottom main line. It's just going the other direction. Can everybody see that? If I know this current, then by default I know this current. That's one thing to remember. Here are the steps to solving the series parallel circuit. So write this down if you want to write steps down. Here are the steps to solving a series parallel circuit if you know all the values of all the components. So if I look at that, I know the voltage value, I know the values of all the resistors, so I can solve it the way I'm going to talk about right now. If I don't know all the values, if I got unknowns, it's done a different way. But I know all the values, so the very first thing I'm going to do is I'm going to identify my nodes. So write it down, identify your nodes. So what I mean by that is put boxes or put some kind of mark so you can name your nodes. So if you drew this on your paper, identify the two nodes that you know exist in the circuit. I'll give you a minute to do that. There's two nodes, and you go to anything in parallel, it's got to have a node on the top, node on the bottom. Call one of those nodes A, call the other one node B. You got more than one, C, D, and so forth. So I got a node right here. I got a node right here. I call this one node A. I'll call that one node B. So step one to solving a series parallel circuit, identify your nodes, say them in a certain color, and then name them, A, B, C, D, and so forth. Step two, go to the part of the circuit furthest away from the power source. Go to the part of the circuit furthest away from the power source and start to combine things. The thing you're going to combine will either be in series. If they're in series, add them up. Or the thing you're going to combine is going to be in parallel. If they're in parallel, use one of your parallel formulas to combine them down to one or down to an equivalent. So go to the part of the circuit furthest away from the power source. If the power source is on the left, you start on the right. If the power source is on the right, you start on the left. If it's in the middle, flip a coin. It doesn't matter. Go to the part of the circuit furthest away from the power source and start to combine things down to get equivalent resistances. So I'll look right here. The voltage source is over here. I'm going to start over here. I'm going to act like this part of the circuit doesn't exist. I'm just going to focus on this. That's all you can see right now, just that part. And act like that exists by itself. And I see that what I have here are two resistors in parallel. Of course, I knew that because I got nodes. Anytime you got nodes, something's got to be in parallel. So what I'm going to do is start with that part of the circuit. I'm going to combine the things that are in series or parallel or whatever it is I'm dealing with. In this case, I'm going to redraw the circuit into an equivalent circuit. I'm going to combine the things that I'm looking at the time right now. I'm looking at R2 and R3. I'm going to combine those into one like I did on the other diagram I just erased. So I'm going to redraw the circuit. Combining these two, and I got to name these in a way that I can look at my equivalent circuit and tell how I got the value. Let me say that again. I got to name this right here in a way that I can look at the name or look at the circuit and tell how I got the value. So what I'm going to do is combine these using the parallel formula. So the way I'm going to name this, I'm going to call this resistor R2 parallel R3. Now what I need for you to do is, using one of your parallel formulas, I got 1.8 in parallel with 2.2. When you do that, you don't have to enter in 1,800 and 2,000. Just enter in 1.8 and 2.2, and you know your answer is going to be in K because both of these are in K. So what is 1.8 parallel 2.2? And you got to be able to do this quickly. I'm not trying to push you right now, but you can't fumble around. You got to be able to get the answer like that because you'll have a whole lot of these to do. So anytime I'm using two numbers like that, it's really quick to hit that inverse X key, or if you want to use product over the sum, whatever floats your boat. But you got to be able to get this answer quick. So what is 1.8 parallel 2.2? How much is that?
Is it 1.76 kilo ohms?
1.76 kilo ohms. Anybody second that? Is that right?
0.99 kilo ohm.
0.99?
Yes.
Anybody second that one?
I got 0.992.
Okay. Now, here's what I do know. I know that resistors in parallel, the total has to be less than the smallest resistor in parallel. So this is 1.8. And so that's pretty close to 1.8. Make you think that's not the right answer.
I
So
accidentally
whoever
typed
gets that answer-
8.8.
Say it again.
I accidentally typed 8.8 instead of 1.8, so they're probably right.
Okay. So we're going to go with this 0.99 K ohm. Okay, so I found the equivalent resistor or resistance, and the next thing you want to do is transfer your node information from the original circuit to the equivalent circuit. So where's node A in this picture over here? Well, you already know I'm using the same color. I use orange for node A, so node A is right here. It's collapsed, but it's right there. Node B is at the bottom of this resistor, so we're going to be at the bottom of the equivalent resistor here. I'm going to show node B right here. Same color. And this right here is that. That's R1. So I'm going to draw this over here as R1. And this right here is that one. So I'm going to draw this as R4. And then what I have on the other side of this is my voltage source. So I'm going to stick that voltage source in there. Now, what I know about these two circuits, guys, is that the circuit on the left and the circuit on the right, they're equivalent circuits. But the circuit on the right is a series circuit, and everybody and their mother can solve a series circuit in theory. Everybody can solve a series circuit. So in this method that we're using to solve combination circuits, series parallel circuits, you go to the part of the circuit, you first identify the nodes, shade them in, name them. You go to the part of the circuit furthest away from the voltage source and start combining it down. And what you want to end up with is an equivalent circuit. In this particular example, I only had to draw one equivalent circuit. But I can have such a complex circuit over here, I might have to draw 2, 3, maybe even 4 of these before I get down to a series circuit. You want to end up with a series circuit, and you don't want to go any further than this. I don't want to combine this and this and that. You don't want to combine it down to one resistor. You want a string of resistors in series, and when you get to that point, you can stop. And what we're going to do is solve this circuit and then go back the other way and start filling in the puzzle over here on the left. So how do you solve a series circuit? Well, it's simple. Number one, find your total resistance. Number two, use that to find your total current. Number three, use that current to find your voltage drops. So let's solve this circuit right here. What I need for you to give me is the total current in the circuit. So go ahead and find the total current for me.
Did you say total current was step 3?
Yeah. So you go through those steps and find the total current for me. Let me know when you got the current. So the first thing you want to do for this circuit, find RT. And then once you got RT, you want to find the current by taking the voltage over the resistance that you just found from the step before. That'll give you IT. And then you can find your voltage drops by taking this current and multiplying by a resistor. But I didn't ask for that yet. What I asked for was the current. So you do this step and this step. So let me know when you got the current.
0.02 amps.
Somebody said the current is 0.02 amps. Anybody second that? Is that right? I'll wait for somebody else to get an answer.
He said 0.02, or did he say 0.2?
Oh, I wrote down 0.2. What did you say?
I got 0.02. I'm just double checking.
Amp. Anybody else get 0.02?
Yeah, I got 0.02 as well.
Okay, so Michael got 0.02. Riley, did you get it?
Yes.
Nathan, are you there? So we got 0.02. So 0.02, that's 20 milliamps. I'm going to take a certain color. I'm going to use this color for current all the way through all my drawings. I'm just going to draw an arrow right here. And I'm saying that my current is 20 milliamps. That's my total current. So pick up one of your coloring pens or pencils and shade in your current arrow a certain color, and it's 20 milliamps. Go ahead and do that now. Once you find your total current in the equivalent series circuit, you want to transfer that current information to the original circuit or to the next circuit over to the left. Now, where should I draw this current in the original circuit? Here's what you want to remember. The current that you get in the equivalent series circuit is always the main line current in the previous circuit. So whatever the current is in the series circuit, you got to draw it coming out the main line in this circuit. So what I know is this is 20 milliamps. And if I know this current right here, do I know this one?
Yeah.
I do. Mainline current. I know mainline currents are equal. The only thing is the directions are different. So if I know that this is 20 milliamps in R1, I also know that the current down here has to be 20 milliamps going the other direction. You see what we're doing here? We're using this circuit to help us solve the more complex circuit, kind of piecewise. All right, so I've found my current. I put my current in the original circuit. I understand that my current that I get in the series circuit is the main line current in the original circuits, or any circuit to the left. Sometimes we'll draw several circuits. So let's say it took me 3 circuits to get to this one. And when I draw that current, I go in each circuit that came before, I draw that 20 milliamps as a main line current. You got to remember, the series current, that's what leaves the battery. It's the batteries that's connected to the main line, so you got to show that in every previous circuit. Now, what else can we get out of this diagram? What's missing? What else can we find? We can find voltage drops, right? I know the current, I know the value of each resistor. I can get the voltage drops for every resistor here. So let's find the voltage drops. Now, what I would recommend doing, you don't have to do it this way if you want, but anytime I have my current in milliamps, if you write your resistors in k ohms, then the math is a little easier, because the milli and the k will cancel. I think I mentioned that to you before. So you do it any way you want, but a really convenient way to find a V1 will be to take 20 milliamps times 120 ohms, or that's 0.12 k ohms. So 0.12 k ohms. And what I was saying is, if you have your current in milli and you have your resistance in k ohms, then all you got to type in your calculator is 20 times 0.12, because the m and the k are going to cancel out. The m is 10 to the minus third. The k is 10 to the third. When you multiply those together, you get 10 to the 0, which is equal to 1. So they cancel. So if you multiply 20 times 0.12, what do you get? Tell me what you get.
2.4.
You get 2.4. Now notice I'm picking up my blue marker. I'm not going to make this is a voltage drop. It's different from a current. It's different from a node. So I'm not going to make this orange. I'm not going to, because when I see orange, now I'm thinking, okay, that's a node. When I see red, now I understand it to be a current. I'm going to make my voltage drop. You use whatever color you want. I'm making it blue because that's what I have. What you say it was, 2.4? What was it?
2.4.
2.4 volts. And what I like to do, guys, and I recommend you do this, not only do I want to color code it, but I usually make my ammeter square. Here's my ammeter square. And I make my voltmeter ground. So here's my voltmeter, and it's going from this point to this point across R1. That's going to help you see how crowded this is getting. We're not done yet, but see what's going on. If you color code it, it's way easier to see. Right away though, as soon as you get this voltage across here, you want to write that voltage in every previous circuit. So right here, I only got one circuit before this one. So R1 voltage drop is 2.4. So right away over here, I'm going to show that this is 2.4 volts across that resistor. Don't solve this completely and then do it. You'll forget something. Every time you get a value here, put it in the circuit before that, all the way to the original circuit. This will help you solve the next circuit, and the next circuit will help you solve the next circuit. What's the voltage drop across R4? 20 milliamps times 0.39 K. 20 milliamps times 0.39 is what? What's 20 times 0.39?
7.8.
7.8 volts from here to here. Anybody else get 7.8? Let's double check these. Michael, did you get 7?
Yeah.
Okay.
Yeah, 7.8.
So right over here, guys, right away, what I want you to do over here in this picture, go ahead and write your 7.8 volts across this resistor. And I got the voltage drop across R4. And let's get the no voltage. Now notice my next voltage is a no voltage, VAB, which means if it's a no voltage, when I transfer it over to the original, I gotta show it going across whatever's in parallel. So somebody tell me, what is 20 milliamps times 0.99? How many volts is that?
19.8.
I got 19.8 volts going from this node A to that node B. So when I transfer it over to my original circuit, I got my draw right smack dab in the middle, and I got to show it going between something in parallel. It's got to be clear that these two elements have the same voltage across them. So 19.8 is a no voltage. So over here, I got 19.8 between this node and this node. And what that means is R2 has 19.8 volts across it. R3 has 19.8 volts across it because they're in parallel. It's a no voltage. They got to have the same voltage. And now I look at this. I see that I got all my current. I got all my voltage drops. We don't do power here. If I want power, you always do power in the last diagram. You don't do it in each previous. That's silly to do that. Get your voltage drops and your currents in every circuit. And if you want power, do that in the original circuit. So I have all the voltage drops and the current. I move to my next picture, which happens to be my original picture. And I say, all right, what don't I know? Well, now that you're taking all these values and you move it to the original, these values are going to help you to solve whatever's missing. Looking at that circuit, what are the only things I don't know here? What's missing? Okay, I heard somebody say it, but his audio is real low. Somebody said the current, I don't know the current in this resistor. I don't know the current in this resistor. So the only thing left to find in this circuit for it to be solved, I got to find this current. That's R2, I'm going to call it I2. And I got to find this current. That's R3, I'm going to call it I3. Now, how do I find current? Well, if I want to find current, I got to know a voltage, I got to know a resistance, and that'll give me current. Do I know the voltage across R2? Yep.
Yeah.
Do I know the value of R2? Yep. I can find the current for R2, I can find the current for R3, and then I'm done. What is my current for? Let's just go ahead and write the formula so you won't get confused. So I2 is going to be VAB divided by R2. That's 19.8 volts divided by 1.8 K. Now remember, if I leave this in K, if I have K on the bottom, when I divide, it makes my current in milliamps. K is 10 to the third, and that's going to come up as 10 to the minus third, which is a milli. So don't write this as 19.8 over 1800, too much work. You do 19.8 divided by 1.8. What is 19.8 divided by 1.8?
11 milliamps.
11 milliamps. So I'm going to write down 11 milliamps, and it's a volt, it's a current, so I'm going to make it square. And so now, guys, at this point, now I can find I3 the same exact way. I can take 19.8 and divide it by 2.2 to get I3. But who can tell me another easier way to get I3?
Subtract 11 from 20.
Okay, I think somebody's audio is messing up, but I think he's got the right idea. We're going to use Kirchhoff's current law at node A. How much current is flowing into node A? 20 milliamps are flowing into node A. How much current is flowing out of node A? 11 milliamps is flowing out of node A. If I want to find the missing current, I'm going to take the 20 milliamps minus 11 milliamps. That's going to leave me with what?
9. milliamps.
9 milliamps. I look at this, I say I got all my voltage drops, I got all my branch currents, I got my main line currents, the circuit is solved. The only thing I can ask you at this point on the quiz or exam or homework, the only thing that I can ask you that I'm not showing, the only thing I can ask you is for power. But for power, the way you get power is you take voltage times current, and if you look, you know the voltage for everything, you know the current for everything. If I want this power, I take that voltage times that current. If I want this power, I take this voltage times that current. If I want the total power, I take this voltage times that current. No matter what I ask you for, you can now give it to me in that original circuit because you've identified all the currents through every element and the voltage drop across every element. Do you guys see how this works now? Do you see it?
Yeah.
Right. So what you got to do, now look at the board. Look at this. This is a simple circuit. Look at that board. There's
Pretty
no
wild.
way you're aware that if I gave you several nodes, maybe 3 or 4, there's no way to grade this unless you color code. You have to color code. Guys, so this is really, and it took the whole period to do one problem. Now here's what's coming next. I don't want to scare you, but once you get good at doing this, and you think you know everything, I'm going to come in here and say, okay, what happens if I put a voltage source right here? What happens if I do this? You can no longer use Ohm's law. We've been using Ohm's law, Watt's law, Kirchhoff. We've been using that all the way through. If I put a voltage source right, it changes everything. There's no way to solve that using Ohm's law. So now we got to resort to more powerful mathematical techniques that we'll learn about later. That's down the road. But the point is, I want you to eat, sleep, and drink this stuff, become really, really good at solving series parallel circuits. I'm just going to give you a couple. We'll do some more. What's today? We'll do some more Friday. We'll do some more Monday. But what I'm giving you on that paper on Blackboard is not enough. You got to do like John has another book. You got to do a lot of problems. Find problems on the internet. Go to your textbook. You got to just eat, sleep, and drink this stuff until you're blue in the face, become really good at it, and then it'll make what comes next a lot easier. This is around the time of the course, and I'm not trying to be funny, but this is where people get confused and they start dropping the course. Some people don't even drop the course. They just stop coming. And then after you end up with a bad grade, and you still have to pay for the course. So if you're going to drop it, you want to make sure you withdraw from the course. But I'm not telling you to drop it. What I am telling you to do is practice. And if you're confused, that's okay, because we still have enough time to turn the ship around and get help if you don't see what's going on. But a lot of it is just becoming familiar with it by practicing it, and you become way, way more comfortable with this. So we'll do some more of this on Friday. Anybody have any questions or comments on what I presented to you today?
I was wondering if you could go over the steps, like the specific steps that you had numbered.
For the whole thing or for
the circuit? I have one, I have three.
Okay, so
I missed two.
here's we'll call it the approach. The approach is this. The approach to solving a series parallel circuit. Now, the first thing you want to do is identify all your nodes. So right here we showed nodes are always in pairs. You can't, right? You always have a pair. You got to have at least 2 nodes. But identify all your nodes. That's the first step. We'll call it a step. Identify all your nodes. And by identify, I mean draw a box around them and label them A, B, C, and so forth. So identify your nodes is the first step. The second step is to go to the part of the circuit furthest away from the power source and start combining things. You'll have resistors in series, you combine them to 1. You have resistors in parallel, you combine them down to 1. So go to the part of the circuit furthest away from the voltage source and start to combine your series and parallel components. What you want to do is keep doing that, keep combining things. Here, it took 1 step to go from this circuit to this circuit, but I can have a circuit where you might have to draw it 3 or 4 times. What you want to do in that next step, I don't know if that was Michael or not, but what you want to do is you want to keep recombining things until you end up with the series circuit. Again, I showed one step here because I can't fit anything else on the board. But in a really complex circuit, you might have to draw 3 or 4 times before you end up with the equivalent series circuit. So you want to keep combining things until you end up with a series circuit. I don't know what step that is, what, 2 or 3?
2. So like simplify.
Simple, there, thank you. Simplify. All right, and then after you simplify, what you want to do is you want to solve the series circuit. And what I mean by solve the series circuit, you want to find your total current in the series circuit. You want to find all your voltage drops in the series circuit. Once you solve the series circuit, the next step is that current that you get in the series circuit becomes your main line current in all the other circuits, all the previous circuits. So go ahead and copy that information over. Make it the main line current. And remember, there's 2 main lines. So once you found this current in the series circuit, you found two currents in the previous circuit. You found this current and you found both main line currents. So the next step would be to transfer all your current information over and transfer all your voltage drops over. And then what you'll do is, say when I solve this circuit, I come over here. When I transfer my information over, I still didn't have I2. I still didn't have I3. Well, now I have enough information from my transfer. I have enough information to solve for those 2. So I will solve for those 2. And then if there's another circuit to the left, I would transfer this information over. And every transfer of information helps solve the previous circuit, if that makes sense. I don't know how you can do that, but does that make sense?
Yeah, it does.
Okay. All right. Michael, you look different in person than you do on camera. I was like, where's the guy? And then, so Riley's he turns his camera on, he's gonna show me his ceiling. I see. I like messing with you, Riley. Michael, you doing? Okay, guys, I actually have an appointment. Michael, I know I told you that I would see you after. I think you have some questions, but I actually have an appointment at 2:15.
Okay.
Not Michael, but John. John, I promise you that I think we had talked. Do you mind if we can reschedule? I don't know,
Yeah.
over.
Do you want to reach out when you have free time, or?
Yeah, it'll be tomorrow. Is that okay?
Yeah, I have math class at 2 to basically almost 5 o'clock.
Well, that actually works out because I have a class tomorrow at 6, and I usually get to campus around 5. So what I can do is send you a link, and we can meet up over. And I'll just post it in case somebody else wants to join. But I'll send you a link, and we can get on camera. We can work out whatever problems you have you want to work out, or whatever you want to talk about.
Are you sure you have that kind of time?
Yeah, it's just around an hour before class. And then if you find that you figured it out, if you don't need me, just send me a text, and I won't put the link out unless somebody else needs to go over something.
I'm sure I'm stuck. So.
Okay, well that's what I want. Get stuck, and you learn when you get unstuck.
Okay.
So guys, thank you so much. I'll see you on Friday. And for those of you that turn your cameras on, I appreciate it.
I just have one more quick question, if possible.
Yeah, sure. Go ahead. Shoot.
What is our homework as of right now? What does that entail?
Your homework is homework 2. Right now, I didn't put a due date on homework 2, but homework 2 is actually due next Tuesday. You should be able to do homework 2 now with what we talked about in the last class.
Gotcha.
So I'll be posting 2 things. I'll be posting homework 3, which is the stuff that we're talking about now, and I'll also be posting. There's another assignment on resistors that's going to count as a quiz. On that assignment, you will have to determine the wattage ratings of resistors and some other few things that you'll have to do for that assignment. So both of those will be due next week, next Tuesday. Right now, all you have is homework 2, though. That's what's on Blackboard.
Gotcha. Thank you.
You're welcome. Anybody else have questions? Okay, guys. Well, thank you so much. I will see you on Friday. Stay safe. And if you need me for anything before then, please send me a text.